Hello and welcome to another SolidWorks video. In this video, I want to go over SolidWorks simulation features, namely the stress and displacement analysis, the finite element analysis type stuff. It is included in all versions of SolidWorks. They call it Simulation Express in sort of the standard version. I have here the educational package, or academic or whatever they actually call it, which includes full-blown simulation. It also includes a feature that uh, the standard edition does not include at all. You have to get up to like the premium or whatever they title the sort of top tier license. And that's the ability to do FEA simulation in assemblies. It's included in educational because educational is effectively the premium edition. It is not included in standards, but the standard single part finite element analysis, the Simulate Express, is included. So for this video, I thought I'd walk through sort of the quick and dirty of how to get that up and running and how to look at the results and sort of what they mean, some tricks. Um, yeah, so let's hop right in. I'm going to go ahead and create a part. And I'm going to start out with just a simple rectangular bar, so we can sort of just have something that we can see, sort of bend. So I'm just creating a bar. So we'll start out with just a rectangle. I am going to give it some dimensions just so that I know what we're talking about. Let's go, I don't know, 2 inches by half an inch maybe. And we can extrude this guy, I don't know, something like 6 inches long. Yeah, I want to see a little more displacement than that, I think. So we're going to give it a full foot. We'll give it 12 inches long. Um, Now, at this point, say, we've been spending days modeling this highly detailed and complicated part that we have in front of us here. The one thing that I always recommend for everyone when they're modeling and simulation is part of the reason, always, at least as a last step, if not up front, give the thing a material. We can do this later. We can do it as part of the simulation. We can even compare different materials, but we need to give it a material. For now, I'm just going to call it alloy steel. Just give it a play. It's just a plain steel. If you look at these numbers and you're familiar with sort of the tensile strengths and stuff of steel, it's just a pretty generic, like average value for steel. And we can tell we applied the material. Notice the appearance changed a little bit because SolidWorks, when you change a material, doesn't necessarily always change appearance, but the built-in ones have. It is in here, appearance. The default ones it comes with have appearances defined, satin finish, stainless steel. So when you apply any of their defaults, it automatically changes your appearance. So we went from like sort of the standard light blue-ish gray, whatever color that is that SolidWorks starts with by default to this, sort of darker gray because it's a steel now. So to start simulation, I actually, in order to start, there we go, needed to get the little pop-up for the screen share to go away so that I could get to my toolbar. That's always good. There's a simulation tab. And again, the Simulate Express might look a little different, but the same features exist everywhere, whichever version we're talking about. We want to create a new study. What we're working with is a study. When we get done, it'll add this into our part file, and we can go back and change things and everything else. We've got other studies available here because, again, premium versions, so thermal and stuff is not part of the normal. Static is pretty much the only thing we're going to get if we do the Simulate Express. But that's going to give us an idea of fatigue, of yield strength, of displacement, bending, that kind of thing. So just going to create a static study, right? I now have a static study down here. And we've got all kinds of options. When I right click, there's, detail properties, function, all kinds of stuff we can do. Notice the first thing now that our toolbar up here is populated is it wants me to apply a material. I've already done that. It already says alloy steel here, so I don't have to do it again. So then in actually our study, we're basically going to go along in the order of these icons that have populated up at the toolbar. So I'm going to add a fixture. A fixture is a part of the part that doesn't move. It's it's fixed. So the simplest way, we need something to not move. If we apply a force to this thing and it's just sitting in space, which effectively it is right now. I mean, as far as SolidWorks is concerned, from a modeling standpoint, we've constrained it to axes and planes, right? As far as simulation is concerned, it's just sitting in space. It's hovering, right? Floating. If we go putting a force on it, pushing down, the thing's just going to fly down. So we need something fixed, something fixed so that it doesn't move. The fixture is probably the simplest way to do that. It's not always the most realistic way to do that, because very rarely is just a certain part of our part not going to move at all. And I'll maybe run either another video or do a second part in this video to sort of demonstrate an alternative that might be a little more realistic. But for now, notice as soon as I clicked fixtures, I get a simulation advisor, and this is basically a wizard that runs us through all the various parts and asks questions and things um, that can help build out a more complex simulation. Honestly, I tend to skip the advisor, the wizard. It helps sometimes, though it's way more confusing than it really needs to be as far as what you're actually trying to do. So I'm just gonna stick sort of over here in this tree, and if I right click on fixtures, I've got all the options. I can just fix geometry. That one is probably, that's the one I'm going to do, but that's probably the most unrealistic, and I'll show you why when we do the simulation. So I'm going to do fixed geometry. Now it wants me to define, and notice as I highlight different faces and edges of this part, I get a bunch of arrows, and those arrows are pointed, if you pay attention, in three axes. So it's telling me that it's going to constrain this thing from moving in all three dimensions, which is kind of what I want. And for now, I just want like this back face. We're going to pretend this thing is, I don't know, embedded in the wall with some mystical physics defying super glue, right? So that face, no matter what I do to this bar, is never going to move, right? No matter what I do. And I'm just going to click the check mark, accepted. It now has a fixed fixture here. Okay. And then, I mean, as far as this first run at a simulation goes, I just want to add a load. So external loads, again, when I right click, I've got all kinds of options, forces, torques, pressures, just plain gravity, all kinds of stuff I can add, right? Again, a lot of these features like temperature and stuff doesn't come in the express version, but forces certainly do. So if I grab a force, again, it's going to want me to pick where that force gets applied. I can pick edges, and notice it'll be at an angle. The purple arrows sort of denote where the thing is gonna be applied. Um, and again, for the sake of just a demonstration of what we're capable of here, I'm just going to grab the top face. Notice all the arrows. That means it's going to put a force pointed down. I can select it defaults to 1 Newton. And I'm just going to switch to pounds. I've got a steel bar. Let's load it with 5 pounds and just see what happens, right? So now I got 5 pounds of force that is going to be applied downwards on my bar. I'm going to accept that. Then the next thing in my sort of tree here, and if you're following along up on we're sort of, even though I'm using the tree, we're sort of moving along these icons. The next thing on mesh, if I can do two things. This thing needs to be meshed. And what a mesh is, we can do simple stress analysis on this thing, right? Simple two-dimensional stress analysis, even a little bit of 3D because we have an area. But we have simple stress analysis we can do on this just mathematically. When we get into 3D, stresses still exist. The definition is still the same, force applied over an area. But it gets a lot more mathematically complicated. So what we need to do is we actually need to create a mesh. And what the mesh will do is it's going to take our geometry and it's going to facet it, sort of like it would do if we transformed this thing into an STL file to print. It's going to create a mesh with a bunch of triangles, and it's going to treat every edge of those triangles like a two-dimensional stress problem. And we could do that mathematically. I don't recommend it. I've done it. It's terrible. Just don't do it. We could do that mathematically because we have just a bunch of force over areas for tiny little sides of triangles. Then when we put them all together over the surface of our entire part, we can see what the whole part does. The computer's really good at that because it can run the math on all those tiny little triangles really fast. That's why we're here in CAD, right? So we can do two things. We can mesh and run all at the same time. In this part, we're done effectively. So I'm probably going to do that, or we can create mesh. Actually, let's create mesh. We create mesh. Um, it sort of tells you, course fine. Usually I leave this as default unless there's really some reason to change it. Um, just click the check mark. It'll think about it for a second, and notice we get all the triangles now, right? So it's not actually analyzing when we hit run on this. It's not actually analyzing the rectangle we drew or the bar we drew. It's analyzing each of these individual rectangles. So or individual triangles rather. It's simplifying things down. Now, I mean, all that's left is to run it, and we can either run it up here again on the icon, or if I right click, I can mesh and run. But since I've already got the mesh, I really just need to hit run. It will think a minute, and depending on complexity, it will take a long time. And you can see it's already done. This is a fairly simple one. Um, and again, depending on the complexity of the part, complexity of the loads, how we've got it constrained, that's it could take. I mean, I've seen it run up to 20 minutes. It's not unusual to see it take a very long time for complex geometries. Um, if I run a more complex part in this video or in a future video, I'll edit that part out and just, sort of mention what it's doing. But anyway, so we have now a bent bar. One thing I want to point out up front is when it shows you this displacement, it is almost, not always, almost always exaggerated on purpose so that you can visualize how it's moving, not necessarily visualize how far. We can tell that up here. SolidWorks tells us right here, deformation scale 714.514. That means however far this is moving, and I'll show you how to determine exactly how far it bent in just a second. But what we're seeing visually is 714 times worse than whatever the actual displacement is. So it is bending down, but it is not bending down physically as far as we see. If I click on displacement, this actually shows us a plot with colors of how far it is displacing. Now, in these plots, blue is always less, red is always the most. And on the end where we're fixed, it doesn't displace at all, right? That makes sense. We told it this end is locked in place. It can't move there. Then at the other end, it's displacing the max. Red is max. That's, it's bending. It's free out at that end, right? Here in this scale is where it tells us exactly how far each given point is moving, and it's based on color again. But the maximum displacement is 4.267 times 10 to the minus 2. That's 0.04 millimeters. And I'm going to grab a calculator quick because I'm not that quick to do it in my head. We started in inches. We might as well end there. 0.04, 25.4. It's bending, bowing down 1.5 thousandths of an inch, right? It looks like a lot more than that, especially this is a foot long bar we modeled. Again, because this is 715 times or 714 times that displacement. And we can change that. I will be honest, though, as I sit here and just came up with the idea to change that. There it is. If we just double click, we can change all kinds of stuff. We can change units. I'm gonna change the units to inches. Just double clicking this was all that opened this window up. If we go to true scale, that is automatically, I'll accept true scale. Notice we changed to 1. This thing popped back up, and it is almost now perfectly in line. If we zoom way in, you might see a very slight gap between our original outline. But notice it's not, it's physically doesn't look like it's bent at all anymore. Because we changed that scale to 1. So if I double click again to open that, change it back, automatic. You can also define a user defined scale instead of 715. Let's, change it to, I'm going to cut that in half just to demonstrate. Let's do 350-ish, right? Now it's not bent down quite so much. So we can change that because again, it's there for us to sort of visualize how it is moving, not provide a true visual of how far it moved. That's what the scale is for. That's what this chart is for on the side to tell us how far it moved. Then, I mean, displacement is important in a lot of parts, how far it moved. Probably more important in mechanical analysis is the stress. So when we check the stress plot, the stress will tell us effectively whether the part's going to break or not, right? Stress strain curve tells us how much load we can handle before we effectively hit the yield point. The yield point, of course, being the point at which it is permanently deformed, right? And then, of course, there's the point where it actually snaps. But yield is usually what we're looking for because yield means our part is no longer able to sort of spring back. It has yielded. It is permanently now deformed into shape. So again, it stands to reason here in any part, the free end has almost no stress in it because it's free. It's able to move. Where we get stress is where we apply a force, but we're not allowing the thing to move, which would be on the fixed end. So this is a check. It looks right to me. The most stress would be on the end of this thing that is fixed. And if you get deeper into sort of the mechanical design, the physics of how beams bend, this also makes sense because the most stress on any beam, and this is effectively what we have now, it's a steel beam, right? Even though it's a bar, it's loaded up like a beam. The most stress happens on the top and the bottom. As this thing bends, again, even though it's not bending a ton, a thousandth and a half, as it bends, it's going to bend the most where it's fixed because the other end is free to move. And the top is sort of stretching out. The bottom, as it bends, is crunching together. So that's where we get the most stress. And in the middle, again, it's very low stress in the middle of any beam. So I mean, just visually, these results check out. And as a total, like the question we're trying to ask, is this part good? Is it safe? Is it going to break under these conditions? Is it adequate for the design? That kind of stuff is what we're trying to answer here. And again, we need sort of the chart to do that. So it's telling us the maximum stress it sees is 2.382 times 10 to the sixth Newton meters squared. And actually, I'm going to change that scale again. I'm going to change it to PSI just to stick with the imperial units. So that 3.4 times 10 to the 2. So 345 PSI is what it's seeing. The yield strength of steel is listed at the bottom. This is the material we chose. The yield strength, 8.998 times 10 to the 4. So quick math, 90,000 PSI on this material. We're only seeing 345 PSI. So we are ridiculously within the strength of this steel, right? This thing is not anywhere near its yield strength. In my head, I'm not going to do the math to tell you how much times. What we can do, though, I won't do it in my head. I'll grab the calculator. Why not? So that this ratio, so the ratio of where we actually are to the yield strength, 8.99880 is our yield strength divided by the 345.5 we see. That is going to get us what is called a safety factor, right? The safety factor is how effectively a ratio, how much over designed are we? In this case, it's ridiculous. It's a safety factor of 260. This thing is 260 times stronger than what it needs to be to survive the load in this application. That's a ridiculous safety factor. Usually, sort of conventional wisdom in mechanical design is we want to shoot for something like 3, right? So we can support enough weight on this, enough force pointed down to get up to, and actually I'd like to try it. Just I'm going to have to guess a little bit. Um, what is 3? If I punch 3 in my safety factor, so it should be able to handle 30,000 psi. Getting that back out to force could be a pain. But I'm just going to guess. I mean, I want to try it. I want to see what we can do. So I can modify this now. Like I know I can handle a ton of force. Where is the thing going to fail, or where is the thing going to hit the 3 times safety factor that I want, right? And 3 times is a good rule of thumb. Um, all I have to do is really just edit this force, edit the definition of the force. There's 5 pounds on it now. You can handle something ridiculous probably. Let's load it with 50 and see what happens, right? 50 pounds now. Accept that. I should not have to remesh. The mesh didn't change. It's still my same rectangular bar, but I should just be able to click run the results. And again, some time will pass. This is relatively quick. We have, let's pop back into stress. So, well, we went up about 10 times on the stress, but I mean, a quick and dirty check. This is 0.3. This is 0.4, right? Times 10 to the third times 10 to the fourth. So this is still 10 times, at least 10 times under the yield, right? It's not going to break. And what is our displacement? I can double check that too. Times 10 to the minus 2. So we only displaced an extra thousandth of an inch. 0.0. Nope, an extra. That's now displacing 0.16. So it's now displacing 16 thousandths instead of the 1.5. So we actually have some bend here. And we might be able to see that if I change this scale to true scale, we might actually be able to see 16 thousandths of motion at a 1-to-1, maybe. Yep. So I've highlighted when I move my mouse, that's the original bar that's sort of highlighted, and you can see it sort of tapered off. So we are moving now at 1-to-1 truly that far, which isn't a lot. It's not a lot. Now, in an application where this is in a machine, is it a lot? I don't know. It depends on the machine. But this is how we can analyze. And I'm going to do this one more time. I want to try to get this thing up near the yield. So let's edit this. Let's drop 100 pounds on it. Okay. Let's drop 100 pounds on it and see, rerun number crunch for a minute. All right, we've displaced. Notice each time I've done this, if you rewind the video, sort of this automatic deformation scale has gone down every time, which means the actual displacement. It's showing us the same picture, but to show us the same picture, the scale has gotten smaller, which means the actual displacement's getting bigger every time. One of those quick and dirty checks. So displacement, where are we at? We doubled again. That's 34 thousandths-ish. If I look at the stress, I mean, we're still not anywhere close, right? We're still a factor of 10 lower. But that is simply how we can um, uh, analyze this stress, figure out if a part is going to fail or not. Of course, this is a very simple geometry. It's a very simple loading condition, but these are the very, very basics. There are some other things we can do. SolidWorks offers the ability like connections. Instead of fixing this end, I can't do it because I don't have the right geometry in a bar. But we have some things where we can do like if we tell it a bolt, we can bolt things together, but we can also do a foundation bolt, and foundation bolts are designed to not move. So I believe I downloaded a part that will allow me to demonstrate. I don't need to save that. Let's see. Downloads somewhere in here, I do believe. Toggle clamp, I did. I downloaded it from McMaster Car. This came from McMaster. Now, I wouldn't normally do a simulation on this the way it downloaded. And I wouldn't do a simulation on this the way that it downloaded because realistically, I want to know individually. I'd rather have this as an assembly. It came in from McMaster as one part. I'd rather have it as an assembly. We could probably make my feature tree bigger here. We could probably break this apart. And I've done similar things in the past on assemblies that I've downloaded from other sources where we can basically delete features and then save as the individual parts and then put it back together as an assembly. I've done that. That's probably the way I would go here. Um, because I really want to know, like, as a part, it will not give me the level of detail that I know I need. As a part, it will not tell me, like, will this pin survive? It won't tell me, will this rubber compress? Because as a part, this whole thing is going to be steel. I can make, though, as an assembly, this can be rubber and this can be steel. And I can see, it'll actually deal with the differences in the assembly level of simulation. But for now, I mean, this is what we've got. I just want to show sort of quote unquote, more correct way to fix things. Because in the physical world, we don't use magic super glue to glue bars to the wall. We use, bolts and things. So first thing I know I need to do what I want to do, I need a plane. And basically the plane is going to act like the wall or like a table. The plane is an unmovable thing. And it's gonna be right on the mounting face. We're just gonna go coincident mounting face of this clamp. And I'm actually gonna rename it table. It's the table that this thing is clamped to. Right? You can see in my window here it renamed. Oops, select it. Make it a little bigger. Doesn't really size doesn't matter. Remember in SolidWorks planes are always infinite. I mean in geometry too, planes are infinite. I just want to make it a little bigger just so I can see it when we get to the simulation. So simulate, we'll do a new study, static again. So this time, um, rather than a fixture, actually I could do it as a fixture because in fixture is a foundation bolt either way. So foundation bolt, or if I go through connections, I'd have to go to bolt and then select foundation bolt. So either way works. Let's do it as a fixture since it's right there. Foundation bolt, same interface. It is going to ask for the diameter of the bolt that the bolt is clamping. And I'm just going to grab one of these slots, right? The diameter or the radius on the end of one of these slots right there. What plane is it clamping onto? And that's going to be the table, right? Now, SolidWorks is going to automatically guess a nut diameter and a bolt diameter. And for reasons I don't know right now, mine is defaulting to millimeters and everything. But this is what we've got, right? So it's going to throw a 1/4 inch nut in, a 0.17 bolt. That's a number 12. This was like the smallest toggle clamp Master had in their catalog, so that wouldn't surprise me. The one thing, whoops, English. One thing that helps too when we're fixing this is it allows us to preload any bolts and really any bolts we put in later. Like if we did assemblies and put bolts in it this way, it would also allow us to preload and probably should because there's almost never a zero torque. There's almost never a zero torque nut, right? We're going to torque it down something. So, I mean, if we give it, I actually looked this up. I did not know this over the top of my head. I'm gonna leave this one in SI because in Newton meters, I actually looked it up and like a light preload is usually considered 1.6 Newton meters. I did not know that. I'm willing to admit I did not know that. I looked it up yesterday when I was sort of playing with things. Um, but that's it. I mean, we're gonna accept that. It throws an anchor bolt in there. Okay. It throws an anchor bolt in there. That's basically, I don't know why it has the little sideways thingy, other than maybe to show us that it's fixed to that plane. I don't know, honestly. I'm going to throw more in because this thing is, we're not going to just bolt this down with one, right? So I'm going to throw 4 more in while I'm here, hopefully really quick. But it's the same thing, just rinse and repeat. Grab a diameter, in this case a radius, grab that plane, which I probably should have made visible to make it easy. Leave that the same. Whoops. 1.6 preload. And 2 more. Bear with me while we rinse and repeat. Copy and paste is so much better, but we can't actually do that in this application. All right, 1.6 preload. And again, that's sort of considered like a light preload on a bolt, which I figured was reasonable just for the sake of demonstration anyway. Plane, we need a plane. That plane and 1.6. There we go. So we should be locked down now. Now I want an external load on this guy. Force, again, I'm going to put it on the clamp, right? The clamping surface. Okay. Now, if I remember right, when I downloaded this, I think McMaster said this thing was designed for 60 pounds, right? That's what their catalog said. So me being an engineer, maybe going to use this thing. I want to see what it does at the max. What does it do at 60 pounds, right? The catalog tells me that's the best I can do. So I'm going to mesh it. Now you don't have to do this in two steps. You can hit mesh and run. But occasionally it will throw errors. If I didn't quite get something right with my definitions, it'll throw an error in that step. Usually you can fight through them. Your results might not be so good, and then you have to figure out why the results are sort of off. But usually meshing alone is safe and you won't get errors, assuming the part geometry is good. See all the little triangles we have now. We should be good. I should be able to now run this study. Rigid wall, okay. We need to define. So what that is telling us, let me bring up the error again. Rigid virtual wall interaction must be defined for a foundation bolt. So we have told the bolts that it is clamping the part to the wall. We have not actually told the part that it can't go through the wall. So we need to go ahead and do that. We are going to do that by adding a connection. And I do believe that is under local interaction. Local interaction, there we go, virtual wall. So we are going to grab these bottom both. Don't forget, this thing is two-sided. I need both surfaces. I'm telling the part right now that it cannot go through the wall. And then I'm going to grab that table plane. So that should be good. Now I should be able to run. Oh, material not defined. I forgot a key step. Like I'm always telling people, define your materials. Let's do it right here from the toolbar. Define material. McMaster just says steel. Like their catalog on this part just said steel. So I'm just going to make it steel. Now wait for my screen share pop. There we go. You guys can't see that, but the screen share pop-up thing is up at the top, and sometimes it just refuses to go away. So we let it run, fun times, let it sit and crunch our numbers. And hopefully we get a result this time. This is sort of the problem with mesh and run. Like you shouldn't have to mesh every time. You should be able to just run once you have a mesh. But if there are errors and you mesh and run, it will mesh every time. And that's really the sort of the bulk of the number crunching in my experience. Um, Now we see it's actually this. So it the first thing it did was and actually I'm getting a notice from Zoom. You guys may not be able to see this. Please move this window away from the shared application. So what it's doing is there's a pop-up up right now um, that says static one and solving. So the first pop-up that now that I'm thinking about it, since it was a pop-up, probably isn't going to show up on this recording. The first pop-up was meshing. It was creating the triangles. This pop-up, which has now been sitting for 39 seconds at 20%, this is where the number crunching is happening. It's actually doing the math. It's calculating the movement, the displacement of each one of those triangles. It's calculating the stress on each one of those triangles, and it's going to put it together into a pretty color map that we can use. And like I said, I'm pretty sure because this solving pop-up that's up right now that I'm just, sitting here babbling while it's running, um, in Windows treats it as a separate item on the taskbar. And I'm pretty sure that since in Zoom I shared just my SolidWorks application, pretty sure that since this pop-up is a separate tab, I think that's why Zoom is complaining at me. Like we're still sitting at 20%. It is now power of the machine. This is where the power of your computer plays a big hand in how fast it can crunch. I'm on a laptop. I'm on a pretty standard, like office user issue Dell. I don't even know, Inspiron, whatever standard IT issue thing, right? It's not a CAD machine. The speed of your PC will definitely influence this process. It's still running. It's now up to 40%. It's literally right now just crunching numbers. But I've still got a big warning from Zoom, big red warning up at the top that I've never seen before that says, please move this window away from, the application you're sharing. So that's telling me that you guys can't actually see the window that I'm talking about. I will have to decide whether or not to edit it out or just keep babbling and leave this now 2 minutes and 30 seconds in the video. I'm leaning towards leaving the 2 minutes and 30 seconds in the video just because I've been babbling. Um, and there's in my mind, I'd have to rewatch. I don't think there's a good clean break for me to cut it out. Uh, and I certainly didn't introduce, I'd have to put like an overlay and edit. I mean, editing. I mean, if you've seen any of my past videos, you can tell I don't like editing. I don't like professionalism in my videos. I definitely don't like editing. So we're now up to 3 minutes. And again, the big part of why this is there's two reasons this is taking so long. Like we saw how fast it did the bar. And geometry does not get much simpler than a rectangular bar, right? So the mesh that it had to create and the numbers it had to crunch were way simpler on the bar. This clamp came in all as a single part, a single component, with all the pins, the handle, the molded, the stampings, all of that good stuff. It had to figure out a mesh for that, which is pretty complicated. Then it has to calculate all of the various stresses as they move through that mesh, which I mean, the more complicated the mess, the more complicated the math it has to do to figure it out. I will say it was doing like I played with this clamp yesterday, and it was doing it much faster. Like we're up to 4 minutes now. Um, it was doing it much, much faster, and I'm wondering if the fact that I've got Zoom on and recording and it's recording locally even that it might be robbing me of even a little more horsepower than I thought. So if this goes up much over 4 minutes, well, I mean, I've already run out of things to talk about, but the cool part about being a teacher is I can make things up to sort of fill the time. If this gets much over, like we're up to 4.5, if it gets much over, there we go. We're back. Pop-up's gone, Zoom warning's gone. We've got results. So now, let's get that model tree out of the way if we can. There we go. We've got results. So we came up with stresses first, right? It popped up with stresses first, and it's showing us how it bent. Our deformation scale is 65, so that's not as big as we saw in the bar on the first iteration when it was only moving like a thousandth, half thousandths, whatever it was. So this one's actually got a little motion to it. Let's check displacement first as far as actual numbers go. So it is displacing, we're still in millimeters. I want to see standard. Show me standard inches. So -3, 1, 2, 3. So it is moving almost 5 thousandths. Now, again, we call this steel, right? Every part of this is steel. If I were to break this apart and rebuild it as an assembly, which I've done in the past, when I was young and had time for such things, I could make this actual rubber, and I guarantee you that that rubber would move a whole lot more under 60 pounds than steel would, right? It's going to compress more. It's also going to take a lot longer for it to crunch the numbers because rubber has a very different material type, different material properties than steel does. It's not rigid. So anyway, we're getting about 5 thousandths of displacement under stresses. Let's check where the stresses are. We can see the benefit sort of the bolts, the anchor bolts. Can I hide those? I've never actually tried. Yes. sort of the benefit, like in the bar, I would, if this were the bar, I would have just fixed these bottom planes, right? These bottom surfaces. Um, and if with the anchor bolts, though, we can actually see that there's quite a bit of stress at those points, and there should be, right? It's pulling up against those. There should be stress. So it's pulling up, and that's the cool part about using bolts and not just fixing surfaces. We can see stress in the fillet here, which we'd expect, right? Wherever there's a bend, there's probably going to be stress. And we can see, a lot of stress here in the arm. And remember what I said, as this arm from this side view is acting like a beam, right? So the top is, in this case, compressing, the bottom is stretching. So that's where we're getting our stresses. In the middle, it's pretty low stress. And that's true of anything that bends. The middle, effectively, I mean, it's hard to see because the colors we're looking at follow the triangles, the mesh that it drew. But if we could draw a line directly through the center of this, we should see absolutely zero stress at the exact center. And that would hold true right up until this thing yielded. Now, it gets, as we get closer to yield, that sort of zero zone gets smaller and smaller. But it's true. It looks right. This looks right to me. Again, we called this steel, so we don't see any stress basically on what would be the rubber cap because we're only hitting it with 60 pounds. But so, I mean, as a quick and dirty first pass, if I wanted to know if this thing could handle the 60 pounds, I'd probably go with yes. We're not, so, quick check and stress, right? Point or 0.8 here, 0.8 here. We're in the same order of magnitude. We're only we're about 2/3 of the yield strength. So we're getting up there. We're getting up there. We don't have much of this. We don't really have a safety factor anymore. We're getting close to yield at 60 pounds, which, as a first pass, again, as a single part, all steel, I would buy that. And I would buy McMaster's verdict that this thing is maxed out at 60 pounds. So that is an introduction to SolidWorks simulation. I hope that was helpful. I hope that gets you started on sort of checking your own designs, whether they're 3D printed parts, whether they're assemblies. Assemblies are far more complicated. I may do another video on that in the future. Thing with assemblies, like I said at the beginning, though, is that assembly analysis like this is not available in the standard edition of SolidWorks. So it's speaking to a smaller sort of user group. But either way, thank you for watching. Hope this was enjoyable. Hope this was helpful. And look forward to seeing you again in a future video.